Okay. Good afternoon, everybody. So let's continue where we stopped last time. And yeah, so basically, when I started talking to you during the first 4 lectures, we usually assumed and we discussed in detail on many occasions this local thermodynamic equilibrium assumption, right? This assumption is very convenient because it allows us to calculate basically everything very simply from very, very commonly known theoretical laws like Boltzmann distribution and Saha distribution and Maxwell distribution and so on, right? And then I said that basically the thing that maintains this local thermodynamic equilibrium are collisions. So if you are in a dense regime, which in practical means for us usually means photosphere. So if you're in a dense regime, then it means that, yeah, it's okay. I was just gonna, okay. It basically means that there is enough collisions to always keep these distributions in accordance with Boltzmann and Saha distribution. And the reason for that is that basically somehow in a way it's always going to be the Maxwellian distribution of your particles through energies that is going to establish that. So you're always going to have things colliding with each other and being in equilibrium with each other, and these things are going to happen, right? And then we took a look at some stronger lines, namely we took a look at H alpha, and there it seems not to work. The mouse is here. Okay, I'll move it away. And then I said that in basically what we call scattering, and I only spoke about scattering on free electrons, which is basically scattering in the continuum. The scattering leads to this non-LTE approximation, and the thing non relates to the local, so things stop being local. And then I gave you this very strong example that if I have very cold gas, but I illuminate it with very strong radiation, and then that gas scatters that radiation, technically speaking, the emission of that gas is going to be very strong, but it's going to be completely decoupled from the local condition. And this is one example of non-LTE. And then the problem that we discussed previously, we made a really simple approximation, and that was that we have some fraction epsilon, which is basically the probability that the photon will be destroyed in absorption process. And then we said that bigger this probability is, closer we are to LTE. For example, if photons are always destroyed, it means that their energy is always converted in the thermal state of the gas, and then the appropriate amount is then turned into emission, but redistributed through wavelengths in accordance with Planck function, right? And that's why we have that I usually call it thermal part of the source function, has this form, epsilon times b, where b is the Planck function, right? But then I said that we have another part which comes from scattering, and in 1D, and if you remember in 1D we said that intensity depends only on theta angle, only on inclination. We would have something like this. We would have that the scattering part of the response function is proportional to the something called mean intensity. So very often this integral here we're going to call J. Mean intensity in this sense meaning angle average intensity. And then I said that the problem is that these two equations, one is the radiative transfer equation, and the other one is, for the moment, I will call it equation for the source function, but you will see that actually the name for this is statistical equilibrium equation. That these two equations are coupled, right? And the essence is that we now have two-way coupling between matter and radiation. Before, if I gave you just the temperatures and densities, for example, from a simulation, you could synthesize the spectrum completely. Now you cannot do it anymore because you need to take account for the coupling in between these two. And now I'm not talking about coupling in dynamic sense. Of course, strictly speaking, radiation has, you remember at the beginning I said radiation is a constituent, but also a probe of the medium. I'm not saying here that, I'm not thinking of radiation in terms of radiation pressure or things like that. I'm speaking about more microscopic effects, that the radiation is ionizing and exciting things and changing this distribution locally everywhere, actually non-locally, because changing it in another form. And something that I really want you to notice here is that now in order to solve the non-LTE problem, we cannot restrict ourselves only to the outgoing intensity. We need to somehow I will say sample, but we need to somehow, because in practice we approximate, but we need to treat the dependence on the radiation on the angle, right? In order to solve the non-LTE problem. And then again, this example, we talked about this before, but I'm just gonna remind you that in principle in LTE, the emission or the source, whenever I say emission, you can say source function and vice versa, whatever you're more comfortable with, because in a way the source function is emission for many of the examples. In LTE, you know things from the local conditions. So high temperature would imply high emission. But in non-LTE, as we said, gas could be cold, but could still emit a lot through scattering process. And I define this epsilon here, which we call photon destruction probability, as the probability of scattering divided by the sum of probabilities of absorption and scattering, or cross-section for scattering divided by the total, or actually opacity, let's call it scattering opacity divided by the total opacity. So these are not really common notations here, but I'm using them just to be super simple and straightforward. I mean, books you might find different notations for these things. And today, so the question is how to solve these two equations when they're coupled. And if you remember in the last class, I wrote them together. So you just move this thing up and you get something called integral differential equation. Differential because on the left-hand side, we have the derivative of the intensity with respect to optical depth. And on the right-hand side, we have the local because we are only integrating this over angle one depth at a time. We have this integral here over the direction, basically. And now I want to stress one more thing. And that is that for this example now, we are looking things at only one wavelength, okay? Because we are talking about continuum, right? So we are talking about, let's say, one given wavelength that we are considering. And that some different wavelengths, we would have some different tau and different epsilon and different b, and these two wavelengths we would solve them completely separately in practice, okay? Some model example for one wavelength. And this is valid for continuum. We will see that for the lines, we can't really treat one wavelength at a time. We need to solve for many wavelengths at the same time. Okay. So the question becomes how to solve that. Yes.
So how is defined epsilon? I think it's the other way. Because if you have pure scattering, epsilon goes to 1.
You are absolutely right. It is the other way. It is absorption divided by the total. You are completely correct. Yes. Yes. So try to remind me this at the end of the lecture, so I edit it and put it edited on the web page. So yes, it is the opposite. Absolutely.
Ivan, can you say this again? The thing you said, if we're in the continuum, we can use one wavelength, but if we do lines, we can.
Well, don't worry about the lines now. We'll come to it at the end. Okay.
Because it's like kind of counterintuitive. It sounds counterintuitive.
Yes, but remember always that in the lines, things change with wavelength very rapidly. So you need to sample the lines to cover all the regimes of absorption.
Okay.
So that's why you need to at least have few wavelengths in the line, right?
So is the tau there number density times the cross section for both absorption and scattering?
It's for both. Yeah. So whenever we calculate tau, we take into account all the opacity sources. Okay. I mean, in principle, you could reformulate it, but it would then make some things more awkward. It's the simplest if you just use total opacity as the total opacity of all the sources, and then you separate, in the source function, you separate the contribution of the thermal sources and the scattering sources. The question is how to solve these things, and the person who solved it, I think the first was Chandrasekhar, who did it sort of semi-analytically. So there is something called discrete ordinate method, and you can find it in his book from there are two versions. I think one is from 1940 and 1950, but I don't advise reading that book now. Maybe it's better for a summer reading because it's super condensed. So that book really, you have to read it very, very slowly. And you really need to know some things in advance, what's going to happen at the end, because it's a really hard book. I mean, this guy was really a genius. And today we won't go through this because It takes a lot of time, and plus it was never really completely clear to me how it is done. So what we are actually going to do, I'm going to show you how it would be solved today numerically on a very simple example. Yeah. Okay. So now bear with me. Okay. Let's take the thing slowly. We are solving these two coupled equations, and the only things that we know are the epsilon and b, right? So these are our input variables. We know, let's say that we know in advance which is the temperature structure of the atmosphere, so we would know B, and let's say that basically from density we could deduce what is this scattering probability everywhere in the atmosphere. But we don't know intensity, we only know boundary condition, we don't know the source function, and we need to somehow basically we need to solve for intensity, because ultimately what we know is ultimately what we want to know is the emergence intensity. But of course, if we know emergence intensity, you already feel that in order to solve for emergence intensity, I need to know all the other ones in between, and then I will be able to solve for the source function. So one way to do it, so now then there is another aspect of this, and that is how to treat this integral here, right? So this equation we solved already when we knew the source function, and we solved it by discretizing in tau, and then using this short characteristic solver. But this we don't know how it happens, and in practice, you basically choose. You say, to have satisfactory accuracy, I have to use these predetermined directions. Let's say mu, so the simplest would be to say, I have mu 0, 1/2, and 1. But then it turns in practice that there are better ways to sample this. There are better quadratures, as we call them. So some of you, I know Momo, for example, is already working with this, so you know that there is like Gaussian quadrature and some other things. Did you guys hear about any of these things before? No. We can discuss it if it comes to the fact that you need it, because these things are very handy for many types of integration. But these are basically the things when some sort of integral is appearing in your physical problem, and you have the freedom to choose discretization of that thing.
Are we talking like numerical integration?
Numerical integration.
Okay.
Yes. So it's a method of accurate numerical integration, which is somewhat better than this. You know about trapezoidal rule. Yeah. Right, so trapezoidal rule is the most basic one. Gaussian quadrature is a little bit more sophisticated because it allows you higher precision with the same number of points. But the simplest thing that we could do here, the simplest approximation for this integral, would be to just take two rays, one going outside, one going inside. So one has mu equal 1, the other one has mu equal -1. And then my intensity becomes the sum of these two divided by 2. And that somehow makes sense. So then what we can do is we could write this, substitute this equation up here and write this in discrete form, okay? Write this differential as a finite difference and write this integral as the sum. And then, okay, so I made obviously some errors here. You would write one equation separately for outgoing rays and for incoming rays. So here we would have, so if you want to have nice centered derivative, it would be derivative in point I would be intensity in point I plus 1 minus intensity in point I minus 1 divided by tau in I plus 1 minus tau I minus 1. And then here I have intensity in the point I minus, this should be epsilon times B, so epsilon times B I, actually epsilon I times B I, and then here 1 minus epsilon, and then 1/2 this, okay. And then I have the very similar equation for the incoming rays, okay. And so in principle, I should change the direction for both the things. I think that here I should have switched one sign. Let me check that. But in principle, you can write these things in discrete form.
Because the minus is...
Because now we're going downstairs, right?
Yeah.
So we will start for I0 and then go then forward. So I need to...
So you're using like 3 points to do the numerical integration.
Yes, I am. Yeah, so in one of these, the sign should be the opposite. But I need to think about it a little bit. And so I will let you know in the next lecture. But the point is that you discretize the differential equation and substitute this with the sum. And then I will have one of these equations for each depth, right? I can write numerically my radiative transfer equation at each depth. And then I will have 2 times number of depth equations, right? For how many unknowns? Where I have I plus and I minus at each depth, which is also 2 times number of depth unknowns. So in principle, and everything is linear, right? So in principle, I have a linear system, and it's not even a very complicated linear system. It's sort of 3-diagonal linear system, because in each equation, the only things that play the role, it's not really 3-diagonal, because you see here I have I plus at 3 points, but then there are I plus and I minus. So if I rearrange it, it would be sort of hexadiagonal, right? I would only have on these 6 along the diagonal unknowns, and there are ways how to solve it. And actually in practice, the first efficient numerical method that did something like this, so not exactly this, is this so-called Poirier method. It's in a very obscure French paper from 1964, so it's very hard to find, and probably you can't really, I mean, maybe some of you can because it's in, but the paper is in French, so I can't read it. But the method is very well described in some of the later papers, textbooks, etc., etc. It is really, really well described. And for example, in a couple of weeks, New Stellar Atmospheres book is going to arrive because I ordered 2 copies. So if you want, you can check there. It's really good. Okay, please. But today, for most of the methods, we don't do this anymore. It's possible, and it's sort of a direct solution, and this is possible because it's linear in the intensity. But in case of the spectral lines, it's not linear anymore. So it's only linear in the case of the continuum, because the source function linearly depends on the intensity. And in principle, in numerical methods, nonlinear systems are almost exclusively solved numerical, because there is simply no such a closed solution. And for example, if you remember from the last lecture, when we set up this ionization equilibrium equation, if for hydrogen only, it is nonlinear, but it is solvable. And if you took a look at the homework, you would probably see that you eventually come to some quadratic equation which is solvable. But as soon as we include more elements, it starts becoming analytically solvable, basically, and you need to solve it. Or more ionization stages, you need to solve it numerically. And it's very cumbersome. And this is true for this non-LTE radiative transfer problem as well. And that's why I'm going to show you how to solve these things iteratively, also numerically, but iteratively, which means you correct the solution through iterations until you are satisfied with it. Because it also because I also find the iterative solution more insightful, because it shows us more straightforwardly what is happening there. And then you can just very straightforwardly generate it to spectral lines. Okay. So I will now have to nurture you a little bit here. So if it's very familiar to you, don't bear with me. And you maybe already know about some iterative methods. So do you know about transcendental equations? Okay. Do you know about nonlinear physics? Do you know about linear physics? Yes. So please, so now that's the question. If I want to fit something with the quadratic function, is it linear or nonlinear? This doesn't have to do anything with the topic, but just it's linear. Very good. Why?
Because you want to find 2 unknowns. You have 2 unknowns.
3.
You have 3 unknowns. Yeah.
And the point of fitting, whether it's linear or nonlinear, it's not whether the function is linear or nonlinear. It's whether the function is linear or nonlinear in the parameters, in the coefficients, right? And every polynomial is linear in the coefficients. Okay, very good. But for some examples, we have nonlinear fitting. And actually inversion, which we will talk about in next lectures, is super nonlinear problem. And that's why we do nonlinear math. And then also solution of huge systems, even if they are linear, sometimes in order to achieve precision, you have to do it iteratively and not directly. Okay. So one example that you probably know about, so I will just go through it more or less quickly, is this one. But one example of, for example, transcendental equation would be this. You can't solve this, right? You can't cancel this thing here. So what I can do is I can start from some guess, and then I say, okay, x is equal ln of 3 minus x. I calculate what would be my new value. Then I substitute that again, and again, and again, and again. And eventually the value of x won't be changing anymore, and I will be happy with it. Okay. And this sounds like a cheating, but it works for so many applications. We have to use these things because we can't. There is simply no solution for this. Right. And we're going to do something similar here. So what I'm going to do is I'm going to rely on the fact that we already know how to solve this equation. Right? We did it in our hands-on exercise. We did it numerically. We even have the tool in the code. And then I can start from some value of this source function, calculate the intensity everywhere at each tau and each mu, substitute this here to calculate this mean intensity, and then substitute mean intensity to get the new value of the source function, and then repeat. And as I said, in principle, to calculate this mean intensity J, we would have to use some sort of quadrature. So we would have to consider few rays going in few directions. And today, radiative transfer codes in 1D use like 6, 10 rays, something like that. In 3D, they use 24, 48, etc., etc. You only consider things in some directions, right? If you are treating the intensity as a variable. But again, for this example, I'm not going to do that. I'm just going to consider incoming and outgoing radiation. So only 2 rays. And in principle, you can do it. And all these results that I calculated for you, I calculated using these short characteristics that we wrote together last Thursday. So there is a Python code on the web page that you can use to reproduce all the images that I'm going to show you now. Okay. And basically, the only thing that we need extra is because now we are going to solve, we need to solve intensity in both directions, outgoing one and incoming one. And we also now need the boundary condition for the incoming one, and obviously 0, right? The radiation coming from the top is 0 because the sun is unilluminated by anything else. Right. So the question now becomes, what is the reasonable assumption? And you need to have a reasonable assumption because, for example, here, if you assume that x is 5, you're going to get x is equal ln of -2, and you're never going to get a good solution, right? So also here, you shouldn't, for example, I think you shouldn't assume that, for example, source function is negative because it cannot be, right? So what people almost exclusively assume is they assume that either source function is equal to the Planck function, but you could also say source function is equal to 0. You could also start from and we will see now the source function is smaller than b and bigger than 0. So in principle, from whichever direction you start, you should end up in a good solution. And the very common test problem that we're going to do here is Planck function is equal to is constant, and the scattering coefficient is constant. And usually for these test problems, you will take something small for this. So for this test problem, I took 10 to the -2. But if you want to play, you can take the code and put 10 to -3, -4, -6. And this usually we put 1 because we don't care. We are interested in the ratio between the source function and the Planck function. But this is, of course, in units of some reference Planck function, which is in SI or CGS units or whatever. So then we start by doing one solution from the bottom. So we do one solution from the bottom to the top. And since my boundary condition is 1, right? You remember that the boundary condition was intensity is equal to the source function. And my source function everywhere is 1. Then it's not surprising that my intensity is going to be 1 everywhere in the atmosphere. That's something very expected. Okay. But the other direction, which is the incoming radiation from the top of the atmosphere, it has different shapes. So I'm starting from 0 now. And I'm integrating, and now note that this is locked out. So at the beginning, I'm integrating over very small steps. And although my beginning value for the source function is 1, because I'm integrating over these very small steps, my intensity is very, very slowly increasing. And until I reach log tau equals 0, I'm not going to have any substantial intensity here. But eventually I'm going to accumulate enough intensity over the path that it will reach 1. But the point is that at the surface, I have 0 intensity coming in, more or less, and 1 intensity coming out. So now you see that if I calculate the mean intensity and the source function, it's not going to be 1 anymore, it's going to be somewhere in between. So this, now what I can do is I can calculate the new value of the source function using the equation, and it would have something like this. So it would be roughly 0.5 at the top and 1 at the bottom, and it would change like this. And now I can do the same. I can calculate again intensity going out and again intensity coming in, but now the things are going to be even more extreme, because now intensity coming out would have less contribution at the top, and intensity coming in would have even less contribution at the top, because I'm starting from the boundary condition 0, and then I again calculate the source function. And obviously, it's not enough to do this once. I'm not going to get the self-consistent, whatever self-consistent means. I think I told you last time what self-consistent means. Self-consistent means satisfying both equations in the non-LTE problem. Right. So we need to do it many, many, many times until the things converge. And this is how it would look. So the source function at the bottom would basically stay the same, but the source function on the top would be smaller, 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 and it would eventually stop changing with iterations. I did it here 1,000 times. Okay. And you see also that this change of the regime is also moving deeper and deeper in the atmosphere, right? So this is how the source function is changing with iteration. And it's always good to look, the question is, when do we stop? When do I stop doing this? And it's always good to track the difference between my new value of the source function and the old one, and usually we call it the relative difference. And if you just look at it like this, it will look like it's converging very quick, okay? But the problem is that what you should take a look at is the log of the difference. And it's changing, it's actually converging very, very slowly. Actually, this should converge like this in log scale, right? And now there is a big question, a big debate about these things, and it really goes beyond the scope of this lecture. But this question of convergence in non-LTE problems is very interesting, and it's what drove people to look for more efficient iterative methods, so-called accelerated methods. But the only thing that I want to tell you here is that, in principle, if I'm converging linearly, so to speak, it just means that even if I reach, like, I don't know, 10 to the minus 4 difference, because I'm converging in such way, it means that if I do many, many, many more iterations, maybe my solution will significantly change still. So I can't really stop very early here. It's not really obvious immediately from the way that I'm saying it now. So we really need to maybe take a look at this more carefully together at some point. But keep this in mind, because you might run into this in the literature when you're reading about this or you want to solve the non-LTE problem. But in principle, you don't want, the only thing that you should remember is you don't want your iterative methods to converge like this. You want them to converge more rapidly. You want the relative change to decrease more rapidly with the iterations. Yes?
So why does it converge so slowly?
Yeah, it converges. I can answer you from mathematical or physical point of view.
Both?
Well, from the mathematical point of view, there is something. How was it called? In principle, you could write this problem as a linear system that you're solving iteratively. And then there is this, oh man, why am I forgetting? There's this characteristic quantity, which basically will tell you how fast your iterative scheme converges. And if you just set it up like this characteristic quantity for this method is super, super, super small. I will look in the literature and I will tell you how it's called. And from the physical point of view, it is very interesting. And for that, let's look at the final solution. So this is the final, let's say, converged solution for the source function, for the dependency of the source function with that. So you see that at the surface, it's much lower than the Planck function. It's like 10 times lower. And then around log tau 1, it's still significantly lower than 1, which means my outcoming intensity will be much smaller than what I had in LTE case. And it reaches value of 1 somewhere around log tau equals 1. Actually, even more, somewhere around log tau equals, between log tau equals 2 and equals 1. Between log tau equals 10 and equal 100. So between log tau equals 1 and 2, which means between tau 10 and 100. The reason for why it converges so slowly would be the following. In these regimes here, where the optical depth is big, you are very close to LTE, but you are not really in LTE. So these corrections to the source functions are going to be very slow. They're going to be very small, and therefore your change is going to be somehow very slow through the iteration. And somehow you can think about it as if you are somehow transporting photons one optical depth at a time. And because there are many optical depths here, because the difference between these points down there is very big, it really happens very slowly. And it's sort of as if I'm, let's think of it like this. So let's look at this evolution here, and let's say I did one of these iterations, okay, and then I updated things, and now I'm sort of propagating these changes between this iteration and the previous iteration, and I'm propagating them very slowly. Okay, and this simplest iterative method is called lambda iteration, and it's named after this notation here. And so far it was very, usually in the textbooks, what you will find is that the textbooks are like this. Textbooks introduce to you specific intensity and why it is there, like we did, and then they immediately introduce this mean intensity to you, flux to you, something called K integral, etc., etc. These are so-called moments of the radiation field. I didn't mention any of these because we didn't need them. And actually, I refrained from even using mean intensity until we needed it, and we need it now. But historically, these things were introduced very, very, very long ago, and this notation, J equals lambda, like lambda operator of S, was introduced by Karl Schwarzschild, who you know from Schwarzschild radius, right? And who was quite a character and amazing person. I don't know if he was an amazing person, but he was an amazing scientist. Yeah, he fought on German side in the First World War, so I don't know. And he actually died from disease in the First World War. But he was one of the pioneers of the radiative transfer. And he wrote this, and after him, this is named lambda iteration, because we are somehow successively applying this lambda operator, which means we are successively calculating mean intensity from the source function from iteration to iteration, right? And actually, the first persons who dealt with the line formation and the radiative transfer were Arthur Schuster and Karl Schwarzschild. So it was really, really the beginning of the 20th century, and then came Eddington, and then came Chandrasekhar, and then came Mihalas, and I became Hammer and all the other people. And we will mention lots of these names. Some of these names. Anyway, this is what. So if you find somewhere lambda iteration, this is why it's called lambda iteration. And this is what method is. So you calculate. You start from some value of the source function. You calculate intensity. You put it back. Calculate intensity. You put it back. You calculate it. You put it back until it converges. Right. And today we have various numeric. So you can write this problem in more rigorously numerical way. And if you're interested into it, we can take a look at it together. And Ryan, I remembered now. Basically, what you do is you write the problem as linear system, then you look for the eigenvalues of this linear system, and the smallest eigenvalue tells you, or the largest eigenvalue tells you how quickly the system converges. And then it turns out that this value here is super large, basically very close to 1. So then it converges super slow. But there are ways how to change the setup of the linear system that it converges faster. And the most common way is this accelerated lambda iteration, which is sometimes called ALI or accelerated lambda iteration, but very often it's called ALO, which is acronym for approximate lambda operator. And this is much more insightful name because, and this is great, and I would really like to tell you about it, but we really don't have time. So maybe at some point we will sit and take a look at this, but it's basically ingenious way how to separate the contributions, the local and non-local contributions in the radiative transfer problem. And it turns out that when you separate out the local contributions, things converge much quicker. And for that, you need this numerical solution of the radiative transfer equation that we did in class. Then there is something called Gauss-Seidel iteration that is also borrowed from numerical algebra, which is even faster way to solve linear systems. And finally, there is something which is called multigrid, which is really advanced. It's sort of advanced because you are, instead of working on only one discretization for log tau, you work on several grids of different coarseness, so to speak. And then you are somehow simultaneously solving the problem on all the grids, and behavior on more coarse grids help you converge faster on the more fine grids. And the person who introduced that to solar physics and radiative transfer was Oskar Steiner from maybe at that time he was somewhere else. I don't know. So, but it doesn't matter. These historical remains are not important. What is important is that the source function is not constant anymore. And this is the most important thing to remember, that even though my Planck function was constant, my source function is not constant anymore. And now if I was going to calculate the emergent intensity, the value would be 0.16. And in LTE, it would be 1. So it would be significantly lower. And if you remember how we came to non-LTE problem, we came by looking at H alpha, and the intensity in the core at H alpha was much lower. The line was in absorption instead of being in emission, right? And for example, Piyush was yesterday in the talk, I showed sodium D lines, and sodium D lines have super deep cores, almost a 0, for the same reason. So does it mean that we solved the problem? So yeah, okay, I showed you what happens when you have scattering, the source function falls down, we have much smaller intensity, hence that explains the spectral lines. And it even explains the wings very well, because wings are formed deeper, right? So wings don't see non-LTE effects, only core sees non-LTE effects. This helps us sort of gain insight, but it's not physically the complete picture. Because, well, we solved the problem here, one frequency at one frequency, one wavelength at one wavelength, right? And this is something that we would call coherent scatter, which means in the scattering process, the wavelength is not changed. And we can look only at one wavelength band, call it, or we only look at one wave. But in spectral line scattering, things are not like that. And now arises the most interesting question for me in the whole course, and that is, what is the spectral line scattering? So very often you go to conferences, you talk about spectral scattering, and then somebody approaches you and pats you on the shoulder and says, what is spectral line scattering? Spectral line scattering is one beauty, and this is the following. So all the time so far, I spoke about LTE, and I said, okay, the atom gets excited by collisions and gets de-excited by radiation, right? Or it gets excited by radiation and then de-excited by collision. And then we have LTE. But of course, it doesn't have to be that way. The atom can be excited by the radiation and then de-excited by the radiation as well. And in principle, there is never clear cut between these regimes. We can make approximations, but strictly speaking, these two processes are always competing. So when I excite my electron by absorbing a photon, it can either de-excite by emitting a photon, and this is sort of misleading because the photon can be emitted in any direction, okay? Or it can be de-excited through the collision with somebody else, some other particle, and it can give that collision energy back to that particle, which you should always translate in your mind that it is giving back that energy to the thermal state of the gas. So now, remember again, if we have LTE and we have this process here, what's going to happen? I'm going to absorb some photons, I'm going to deposit their energy into the gas, and then I'm going to take that energy back and emit it, but that emission will be following the Planck function, which follows the temperature, the local temperature of the gas, right? Because in LTE, we are always assuming the thermal energy of the gas is much bigger than the energy of the emitted and absorbed photons. Basically, the photons are some sort of small collateral damage there. They are being absorbed and emitted, but their energy is so insignificant with respect to the thermal energy of the gas that that there is never heating or cooling, and the Planck function is always constant and nice and beautiful and follows the local temperature of the gas. When I have this situation on the left, my photon is basically preserved. And if I have a bucket load of photons being absorbed and then emitted, then my emission can end up being much bigger than what Planck function predicts, for example. And this thing on the left is what we call spectral line scattering. It's not technically scattering, it's absorption followed by emission immediately, but we call it spectral line scattering. But of course, looking in really quantum way, you could also treat continuum scattering as this, if you introduce these virtual states. And actually today a friend of mine on Facebook asked about virtual states, so we are going for the beers after the last talk to discuss that. And this is very it's very advantageous to look at things that way, as if it was scattering, because it's really what happens in the scattering process. The photon is preserved, and of course, as I said, it can go anywhere you want, but the point is that the photon is preserved. And this also tells us why scattering breaks LTE, and because it creates emission which is different, right? And I mean, it can also create absorption which is different, because in principle these things are not only populating the upper level, they can also depopulate the lower level. So it's yes.
So you're saying that I can be in a region that has a Planck function.
Yes.
And the emitted photon would be a specific photon, okay? But then if an absorbed photon has come from another place, and that's the one emitted, it has no connection to the Planck function.
Exactly. Exactly.
But it's still emitted from there.
But it's still technically, geographically emitted from there, right? Okay. So, very good. The point is, of course, we're going to have two different regimes depending on which of these processes dominate, right? If there are a lot of collisions, then excited photon won't have time to radiatively de-excite, and this will happen and we will have LTE. On the other hand, if there are not many collisions, then these processes will emit, and then this immediately gives us answer why is LTE important for chromospheric lines, because they are formed in the regions where the density is much lower, where basically the atoms have the time to de-excite radiatively. And of course, the non-LTE are going to be more prominent for the lines which have a bigger Einstein coefficient of spontaneous emission, because the Einstein coefficient of spontaneous emission tells you how fast you de-excite, and the faster you de-excite, the less you care about the collisions, right? And that's why forbidden lines, you only see them in super dilute medium, like the planetary nebula, because they have so small even very dense, even a little bit dense medium is going to depopulate them collisional. And then we only see forbidden lines in super dilute things like corona or things like planetary nebula and things like that. Okay. So we were basically talking about this right now. Here, so this is just a refresher. Yeah, so now I always speak a little bit disconnectedly because I start explaining something and then I realize that the summary of that on the next slide, and the presentation mode here is such that I'm seeing the same thing here and there. Right. Okay, so in a way, this is important thing, that the photons are somehow preserved. That if I'm shooting photons from a very bright region and they're mostly scattered, their distribution is somehow preserved. Okay. But now a very important question comes, which we need to answer if we want to really correctly treat spectral line radiation. And that's what happens with the wavelength of the photon. Because from this picture here, you would think that the wavelength of the photon is exactly preserved. And you would think that this coherent scattering that we treated before is a good approximation. But it's not really the case. Because for the most spectral lines, what actually happens with the atom while it's excited is that it still suffers some collisions, but these collisions are not of high enough energy to de-excite the electron, the atom, but do have a big enough energy to slightly perturb its energy state. So strictly speaking, I'm exciting my electron, it ends up in this energy state here, up there. And then let's say that it will be exciting 10 to the minus 8 seconds. But during these 10 to the minus 8 seconds, nothing hits it so strongly to de-excite it completely. But there are some particles with weak energies which hit it with big enough energy to slightly perturb the energy state, because we said that energy levels are not infinitely sharp, right? And then basically the wavelength of the emitted photon slightly changes. And in principle, how we would call this thing is we would call it redistribution. So photons are absorbed following their, basically photons are absorbed according to the absorption line profile, right? I will absorb more photons in the line core than in the wings. But then what happens with these photons is that they are redistributed. And what we usually assume is that the atom it's not atom, it's atoms. It's always an ensemble of atoms. This ensemble of atoms, it forgets about the wavelengths of the photons, and it redistributes, man, this is a hard word, redistributes them according to the emission profile, basically, or absorption profile, which are in this case the same. So I absorb photons, and so there is bigger chance for me to absorb them from the line core than from the line wings. But then again, when I'm emitting them, there is bigger chance for me to emit them in the line core than in the line wings. But so now when I say that way, you're like, okay, but it's like the same. But it's not really the same, because usually in the wings I will have more radiation absorbed, because generally in the wings of the line, the intensity is higher because it comes from deeper regions. So I will absorb all these photons from the wings, and then we'll re-emit them in the core, right? So this redistribution, it plays the role. And this is exactly the point, that the photon, which is absorbed in the wing of the line, it will still be most probably emitted in the core of the line. But again, the photons which are absorbed in the core can still be emitted in wings. Yes, Piyush?
When you're saying line core, you just mean the wavelength, not the location.
I mean the wavelength, yes. Okay. Yes. I mean the
wavelength. That thing is just going to be magically get to the chromosphere and then...
No. This only happens bit by bit, right? So this is a very useful approximation, which we call complete frequency redistribution, or CRD. And it's frequency because, as I told you, in most of the theoretical books, people work with frequency, but it's still the same. And this complicates the situation because we cannot now treat each wavelength separately, like it's coherently scattering, because obviously when I absorb, I'm going to mix all the wavelengths and I'm going to reshuffle them, right? So now I need to discretize my line in several wavelength points, typically 10, 20, 50, for some very strong lines, 100, 200, 500. And then I need to solve for all these wavelengths simultaneously, which means the size of my system increases by this factor of number of wavelengths. Right?
That's a big factor.
It's a big factor, right? And I just want to stress that in principle, this is also an approximation. And this is valid for most of the lines that are formed in upper photosphere, lower chromosphere. But for really super, I would call them usually extreme non-NLTE lines, such as magnesium HNK, calcium HNK, Lyman alpha, helium Lyman alpha, etc. These lines are formed in such a dilute medium that you can't even count on these small elastic collisions to shuffle the line. But you reach some regime which is very exotic, which we call partial frequency redistribution, and which is really, really tricky and cumbersome to treat in non-LTE, but is really crucial for modeling of some of these lines. So you're not going to get the correct line shapes if you don't take this effect into account. And then that effect sometimes becomes even so prominent that not only the wavelength redistribution becomes important, even the direction becomes important, because strictly speaking, isotropic scattering is not a complete picture of the problem, right? You remember maybe from optics that if you have scattering on electrons, there is this spatial distribution function, which gives you bigger probability for forward scattering and smaller for 90 degrees. So if you really want to model spectral lines in great detail, you need to take into account the whole. And then it becomes really hard, but also really rewarding, because you get to see many beautiful.
So even like the dipole, how the dipole radiates.
Yeah, but it's not even the dipole, because it's a spectral line now. So there are some quantum effects. I mean, it still behaves like a dipole mostly, but there are some corrections to the dipole because the bound states are now more complicated. Okay, good. So what is the quantity that we now need to take into account? So, well, sort of the key quantity when we had the coherent scattering was the mean intensity, right? And I wrote the equation here for the case when it depends on both angles, but for us it usually depends on mu only, so it was 1 over, there is integral missing. Oh, okay. So there is integral here, of course. 1 over 4 pi integral, blah, blah. And when we had 1D case, then it reduced to mu. Now we also need to, we are going to have a different quantity, which you can informally call mean intensity, but I prefer to call it scattering integral. And the scattering integral is the integral over specific intensity, over directions, but also over the line profile, which means I multiply intensity with my line profile times d lambda, and I integrate all that over wavelength and the direction. And in 1D, it would look something like this. And I coded this equation like 1 million times in my life. And you probably will at some point. So this is what the mean intensity, or sorry, scattering integral is in the non-LTE case. And this scattering integral, yes?
Why are the bounds like that?
What should they be?
Like from the center, some distance left and right.
But it doesn't matter, because this profile will drop to 0, right? So in practice, this is of course never going to be from 0 to infinity. It's going to be from minus 5 Doppler widths to 5 Doppler widths, or minus 10 Doppler widths to 10 Doppler widths, or minus 100 Doppler, depends on what you want to do.
Right? When you code that like in a numerical code, you pick, right, when the profile goes to 0.
Yes, you say I'm gonna forget about this when my profile drops to 10 to the minus 5 or something. And you also choose the sampling according to the accuracy that you want. You say I want to get from this point to this point with steps this big, or a little smaller, or a little bigger. And then you can again do various quadratures for this, but Because in practice, this becomes much more complicated. Not from the conceptual point of view, just from the amount of things that you put in there. So for this integration over lambda, we usually still use the good old trapezoidal. Right. Okay. So what does this scattering integral, what role does it play? Because now we don't have such a simple equation that source function is equal something epsilon times b plus minus epsilon times k. We expect something more complicated. And it's true, we now work with something called rate. And basically what this scattering integral will tell us is going to give us a rate. And what are rates? Rates are basically how probable, you could say how often something happens or how probable something is to happen. And we were talking about one rate, and basically Einstein coefficient of spontaneous emission is a rate. It tells you how often the de-excitation happens, right? And now we're going to introduce two more rates, and I call them radiative rates because they tell you how often some radiative processes are happening. And these are going to be rates of stimulated emission, which is going to be equal to Einstein coefficient of stimulated emission times the scattering integral, right? And rates of absorption, which is going to be Einstein coefficient of absorption times the scattering integral. Okay, and you somehow intuitively feel that, right? Because this scattering integral tells me how much absorption and stimulated emission processes I have. The more intensity I have, the more absorptions I have. The more intensity I have, the more stimulated emissions I have. And why are we now working in terms of rate? Because now we want to see explicitly what happens in the atom. How often does the atom radiatively excite? How often does it absorb? How often it stimulatedly emit? And then how often do the collisional things happen? So we are going to also take into account collisional rates. And these collisional rates tell you, okay, their units are also going to be second to minus one, and they tell you how often does my atom excite in collision with other atoms? How often does it de-excite in collisions with other atoms? And in principle, for most spectral lines of interest, these collisional rates depend on the electron density. Okay, which then again tells you why in dilute medium I have less collisional rates and I have more non-NLTE case, and they somehow depend on temperature, usually in some power law. And I don't remember what should that here, maybe like 4/3 for like the most common case or something like that. So the higher temperature there is, basically things collide more often. It's simple. And then what we're going to set up, actually the next approximation that we're going to do, because now it slowly starts becoming clear that what will govern my populations is not going to be Saha equation, is not going to be the Boltzmann equation, it's going to be these rates. Because if I'm de-exciting things much more, if I'm exciting things radiatively much more than I can de-excite them collisionally, something is going to be disturbed, right? And then we're going to write such a system of equations, which we call statistical equilibrium. And in statistical equilibrium, we assume that the populations of the individual energy levels are constant in time. And statistically, basically, sure, things are transiting, but on average, each population is constant. What does it mean? It means that basically the sum over all the processes that are populating my level, Ni, has to be equal to the sum of all the processes that are depopulating that level, right? And here in these, so R stands for, surprise, surprise, the radiative rate. C stands for surprise, surprise, collisional rate. I have to add here all the collisional stuff and all the radiative stuff to see how many electrons are basically coming from all the other J levels that I'm considering to my level I. And here I'm summing all the electrons per second that are going from my level I to the other levels J. So that's why I need to multiply the rates with the level population. And then I'm summing here level, I'm going to get a linear system, and I'm going to have one of these equations for each level, okay? And I'm going to get a linear system, and then when I solve that linear system, I'm going to get the population. Well, why did I write all this when this maybe is simple? Well, it's not simple because, I'm sorry, I jumped the gun. Yes, go.
So how do we know this whole thing converges?
It does, well, wait, we still didn't mention the convergence. We don't know. So the point, and Momo hinted it now, is that to get the solution of this system, I need all the rates. But as you remember from the previous slide, to get, I jumped there. So from the previous slide, so the rates depend on the intensity, and then the rates give me the level populations, and the level populations give me opacity and emissivity, which gives me intensity, which gives me rates, which gives me this. Or looking the reverse way, to get these, I need the rates. For rates, I need the intensity. For intensity, I need opacity and emissivity. For opacity and emissivity, I need the level population. So there is coupling again. And it's more complicated now, and it's more nonlinear. And it's more nonlinear. It's simply nonlinear because now, for example, if I'm looking at this atom here, you can now imagine that there are more levels below up and more levels below, and me disturbing this thing here is going to disturb all the other ones and the lower ones. And if I, for example, mess up with the population of this level, it messes absorption in this line, but emission in the other line, etc., etc. And the things become nonlinear. And another thing is that, strictly speaking, now I need to treat all the relevant levels. Even though I may be interested, let's say that this is H alpha, even though I may be interested only in the spectrum of this line, the populations of these two levels are going to depend on all the other rates between all the other levels. And I need to treat much more levels and the radiated and collisional transitions between them. And that's why non-LTE is such a pain, is that even I'm only interested in calcium infrared, I need to model UV transitions, optical transitions, infrared transitions, microwave transitions, God knows what, right? Ionizing this. And another thing that I want to stress is that in this linear system here, I only was focusing on the line processes, but in principle, you also take into account ionization. So there are these collisional processes also for ionization, both collisional and radiative ones. So in principle, these levels here should also take into account ionized states. So for example, I could say I'm treating 5-level hydrogen atom plus continuum, which means I have 6 levels in total. Ground level hydrogen, first excited, second excited, third excited, fourth excited, ionized state. And then I write all these rates between them, and then I solve it. And the way we solve it is, again, iterative. It's, again, we assume some starting level populations, which usually, again, are assuming to LTE, and then we do things again and again. Okay, so now let's answer Momo's question. We don't know. We don't know. And in principle, I think you could even have some setups where these things numerically won't converge, really. And the most of the studies, I mean, the point is that if you treat, if you simplify this problem to the problem of 2-level atom, something, then you will get a linear system again, which is very similar to this continuum that we solved in the first half of the class, except there will be one extra integration in the wavelength and nothing else. And you can very easily take the code that I have posted online and generalize it to that. The solutions look a little bit different, but the messages are the same. And that's linear, and there you can study these convergence properties, again, looking at these eigenvalues, etc. The people who did that, I think it was Auer and Javier Trujillo Bueno, and the people in the 80s and beginning of 90s.
Yes.
Studied these things. Nowadays, people don't mention it very often, but we can. I could refresh on that, so we could have a look at that. But nobody really did study on these nonlinear problems to see how how they converge. I mean, it's only mostly practical. So if you see that you're not converging, then you usually disable acceleration, or you relax the solution, as we call, which means you correct by less than you would correct otherwise, hoping that you get to some nice behavior. But sometimes these things are really problematic because eventually you have to solve a linear system here. So now I'm going into some numerical detail, but for me it's really interesting. Sometimes you need to solve this linear system here, and it can happen that it's ill-posed, that the solution should be something, but your numerical method simply can't handle it because the values are different by order, many orders of magnitude, and you can't get good things. So very often it happens that people just have to simplify their problems in order to solve. And it's sometimes very tricky, and there is no really general, very good way to solve it. Yes?
So I guess I want to rephrase my question. Is this numerical setup going to have a unique solution?
Yes. If it converges, it should always converge to the same one. There are no multiple minima, so to speak.
Okay.
At least not that I heard about it, and it shouldn't really happen. I mean, it should.
There's more than one atmosphere.
No, that's a different problem. It's just simply for one atmosphere, for one setup, you shouldn't have more than one solution for the level populations that satisfy physically feasible. Maybe there is something like with negative populations and things like that that could satisfy it, but I think you're never going to reach it.
So just because if you have like a lot of different transitions, I'm just thinking.
That's a very good question. That's a very good question, and I never thought about it, and it could happen.
Yeah. Because in the two-level often it's very easy to show that like the biggest, like the all eigenvalues are negative, so it's not going to go up.
Yeah.
But once you start getting that non-linear.
Yes, but I don't know what are, from the point of numerical analysis, what are the ways of like treating the problem of convergence of a nonlinear system. How do you study it? And also we very indirectly see that it's nonlinear, right? You never really explicitly write it as a nonlinear system. I mean, you could write it, because the nonlinearity, where does nonlinearity come from? It's nonlinearity in levels, because these levels, they create source function, and they create opacity and emissivity. And sometimes one level is going to contribute to the emissivity, in the other terms in opacity, so sometimes it's going to be in this denominator of the, if I know the word, denominator of the source function, sometimes in the numerator. Numerator and denominator of the source function, right? So it's going to be tricky. It's going to be tricky, and well, it's something that we could take a look at together, and I'm sure the kind would be very useful. Yeah. Yes.
Basically, like, I don't know, I haven't taken numerical methods for like 3 years, but I remember that when you write some Taylor expansion or something of your system, then even if it's nonlinear and you keep like third order terms, then your mistake is the fourth order term.
Yes.
So basically, we can find the error, but we don't do it. That's what you mean in practice?
No, it's not a question of error, because the point here is that the point in iterative solutions is going to be that it's going to converge to the true solution eventually. It's going to satisfy it to many digits. It's not the problem. It's just the problem that you can't solve it directly, right? Because you don't have, you don't have general, for the fourth order equation, you don't have the direct solution, right? And here when you have many levels and you write these, and then you switch in like the source functions and things like that, it becomes nonlinear but also non-local, because radiative transfer is coupled. It not only couples all the level populations at one point in the atmosphere, because in these radiative terms I get intensity, which is the result of the radiative transfer to the whole atmosphere. So my non-LTE problem couples all the points spatially and all the levels of the atom. So it's really super annoying. So basically you need to simultaneously solve for number of depth times number of levels unknown. So that's why you mostly do it not mostly, exclusively do it iteratively. But there are some examples where we can learn a bit by just looking at very simple problems. So So let's say that you have a solar prominence. So solar prominences are very dilute bundles of chromospheric plasma that are for some reason suspended in corona or transition region. And how do the prominences? They mostly reflect the light, right? So let's try and think about that reflection in terms of non-LTE, because we see them emit, they see them produce emission in spectral lines. If I said, for example, the prominences are so dilute that there is no collision there, okay? And if I say, okay, I'm treating wavelengths where there is no stimulated emission, the only things remaining here, so I delete all the collisions, I delete stimulated emission, is what? Is absorption and the spontaneous emission, right? And they're competing. Stimulated, if I'm looking at the lower level, for example, of the transition, stimulated emission is populating it, and absorption is depopulating it. So I have this thing here, right? This is how often it's being populated. This is how often it's being depopulated, right? And then, basically, what I have, this here then is what? Is proportional to my emissivity, right? My radiative rate of de-excitation is proportional to my emissivity, which means that my emissivity is proportional to my mean intensity that is illuminating my prominence, which is very similar to the case of coherent scatter, except that if we had coherent scatter, what would happen? We would have more or less we would have every wavelength reflected as it comes. But here what happens is that we're still going to have this redistribution. So we're going to gather all the absorbed intensity in this scattering integral, and we're going to redistribute it according to the emission profile, right? And you can see this, for example, in sun, it's maybe not an obvious example, but the difference between line scattering and coherent scattering, you can see it if you consider an example of, for example, well, you can also see it in the prominence. Can we really see it on the prominence? If I have just electrons, right, and I'm illuminating my radiation by absorption line, what's going to happen? I'm going to absorb more, I'm going to reflect more light in the wings and less in the core, because there is less light in the core and more in the wings. So I'm going to see reflected absorption line. But prominence, even though I'm illuminating it by absorption line, there is going to be redistribution, so I'm still going to get an emission line. So it's not immediately obvious, but there are very important consequences of the frequency redistribution. And that's why you will always see, no matter what I illuminate my prominence with, I'm going to see an emission line like this. Okay?
So why can we ignore stimulated emission here?
Well, we can't really. I mean, we can because it's small. Okay, actually, maybe at this wavelength, this is 1080, this is like 1 micron. So there is, so maybe important. But for example, in optical, if you were to analyze the differences between these two, you would get that the stimulated one is much, much smaller than this and much, much smaller than this for all reasonable values of J. Like, of course, I can always pump so much radiation in my atom that stimulated emission becomes important. Right? But it's more important than microwave. That's microwave. Okay. Good. So, where were we? Prominence radiation, and then what happens here? So here I just found what I told you before. We need to solve this problem, to get layer populations, we need radiative rates. For radiative rates, we need radiation. For radiation, we need a Bastian emissivity. For that, we need this. And we are in the problem, and we will solve it iteratively, right? And for this, you can use lambda iteration again, and it would be the same. You start from a very simple solution. You start, for example, from the level populations following LTE. You solve, you get, and then what happens? I mean, we still didn't talk about consequences of this. What's going to happen is that when you start from this LTE populations, again, you're going to have less intensity in the top of the atmosphere, general. And then it means that basically your levels are going to be underpopulated. So now we can understand better why the source function is dropping. My levels are going to be underpopulated because I have less intensity. There is less radiative excitation to balance radiative de-excitation. Because still, think about this. It's very important for understanding the line. If I neglect stimulated emission, basically my amount of de-excitation doesn't depend on the radiation field anymore. It just depends on the Einstein coefficient, which is a constant. So then, if I have if I don't have enough radiative excitation, my upper level is going to be depleted, right? And I'm going to get the source function, which is smaller. My emissivity is going to be lower. My source function is going to be lower, and I'm going to get this characteristic shape where the source function drops down. And people wrote so many books and so many papers on numerical methods, on like analyzing the things, on effects and this line. And many of these people were in Boulder at this point or the other one. And here I'm listing like just some suggested names. And maybe the most important papers and books are these three, like by Cannon, Sharmer is Joran Sharmer of SST, Rybicki and Hammer is Rybicki of radiative processes, and Hammer who was here. And they wrote like most important papers which treat really this problem and explain how to converge, how to accelerate the convergence, what is happening, how to set up these equations, etc. Then there are books by Mihalas, are the most stellar atmospheres that you probably heard about, which is full of information, but you need a long time to read it. But in the second part, there are excellent problems. So in, for example, in Germany, there is this practice of preparing for your defense, because in defense they can ask you whatever, and then people usually prepare from there, because then it also gives you insight into the stellar atmosphere problem. So I don't know, if you have time, it's worthwhile always to look at it. Then you have the papers on codes, and the two most well-known codes today for non-LTE calculations are RH, which comes from Rybicki Hammer, because it's written after that paper, by Heinrich Utenbroek. Except he also treats some more sophisticated physics things there, and multi, which comes from multi-level, written by Carlson and Sharmer, which was, I think, actually PhD thesis of mine. And then there are many, many other names, which I just wrote here out of melancholy, or however you want to call it, but yeah, you will recognize maybe some people who were involved. Okay, very good. So you can solve that. We know how to solve it. It would take us too much time now to discuss it. There are books written about it. There is a famous, well-known book called Numerical Radiative Transfer by Wolfgang Kalkofen. And there are like 10 papers there by all these names on 10 different numerical methods to solve non-LTE problems. But what I want to talk about you more today in these last 10 minutes is like what are the consequences, what we see in the sun, and what are some ways to understand it. So this is for me, one of the most beautiful illustrations of the non-LTE problem. So there was this school of radiative transfer. I was a very small kid then. It was in the 90s. It was organized by Matt Carlson, and Rob Rutten was one of the lecturers there. I definitely recommend, and I mean, I recommend many times Rob's book, but for non-LTE it's very good. He understands it very well and he teaches it beautifully. And somebody made this poster, and this poster really tells you what's happening. So you see here these little things here. They should represent photons. And on the right we have the inside of the sun. On the left we have the outside of the sun. And this line here is more or less the photosphere. And then what happens is that as we are going outside, it's easier and easier to photons to escape. They have a longer and longer mean free path, right? And then as we are going towards the surface, the density of photons decreases. And you can think of density of photons as the mean intensity. Mean intensity is somehow proportional to density. And then because this mean density drops, the source function also drops, and we have this characteristic non-LTE effect in the sun, that the lines have much deeper cores than what LTE predicts. And it's really true. And this is the plot for magnesium B, for the line that we had it for the hands-on, we didn't recalculate it, and it tells you the difference between the blue is the source function in the log scale, and the orange is the Planck function. So it's many, many orders of magnitude region where the line forms, which if you remember was around 1,000 kilometers. It's much, much deeper, and you see that the line goes in the absorption. And then now we also need to understand better this formation of magnesium H and K lines, which were these very interesting lines that were going in absorption, then emission, then absorption again. What happened with them is that if you look at the source function, is that up to some point, which is here, it follows the Planck function. So it can capture a bit of a temperature rise. But eventually the non-LTE effects kick in here for this line. And when non-LTE effects will kick in, it depends on a lot of things. It doesn't only depend on the collisional coefficient, it also depends on the strength of the line. Because there is one thing that we didn't discuss a lot, and that's that even if I had a lot of scattering, I still had my source function equal to my Planck function deep in the atmosphere. And the reason for that is that deep in the atmosphere, things are opaque. And even though they scatter a lot, photons are still captured there. They can't escape. So they are scattering, but the things are opaque. And that is what we call sort of effectively thick, which means it's thick, there is scattering, but it's still so thick that the photons are trapped there. And effectively thin would be the object which is actually optically thick, but there is so much scattering that photons still can escape through multiple scattering effects. But okay, this is now too hardcore. Let's just understand this more. So here the non-LTE effects kick in, the source function drops down, and we see the absorption in the core. And we get these shaped lines. And we really see them in the sun and also in the other stars. And they give us a lot of diagnostics about the atmosphere. And now we can also understand what's happening at the H alpha. In LTE, H alpha, because it forms very high, like 1,500 kilometers or something like that. So almost in high chromosphere, almost in transition region, we see that it goes very high. But in practice, there is so much scattering that it allows all these photons to escape. And the equilibrium solution is actually that the line core lies much lower. Because simply the upper level, the n equals 3, is depleted. There are not enough photons to populate it because these photons escape. And then what happens is that we have the lower source function, we have the drop of the source function, we have the absorption. Very good. So, to conclude, that we are done here with the line processes, with LTE, non-LTE, and all these things. Generally, for many lines, photospheric lines, moderately strong lines, weak lines, LTE is a very good approximation. There are sometimes some subtleties which we didn't discuss enough, like for example, iron is very susceptible to photoionization. So even though it can happen that Boltzmann statistics is valid, but then the Saha is not, because there are more photoionizations than what LTE predicts. And also the opposite things can happen. It can happen that the specific atom is basically in LTE concerning the ionization stages, but the levels inside are redistributed according to that they don't follow Boltzmann statistics anymore. And it can also happen that because the ionization stages don't follow LTE, that some parts of the continuum don't follow LTE, and it happens in UV. You have this so-called non-LTE continuum. The whole big parts of the spectra have much different opacities or emissivities than what LTE functions, and then what LTE works. So you could basically create your own plots of this kind. You have the actual non-LTE opacity and emissivity for the magnesium B line in the exercise. So when you calculate it, it will come out in non-LTE because they calculated it in non-LTE. But if you replace the source function everywhere with the source function of the continuum, of the first or the last point, you will get the line in the emission instead of the absorption. So you can convince yourself what is going on. So this was it for today. Questions, comments, suggestions, etc. I need to sit, I'm not really emotionally involved. Okay, then let's spend a few minutes talking about what we're going to do next. We know now, basically, we have the picture, how the lines are formed, what are they sensitive to, and what intricacies are involved into their calculation. We now want to extend the problem. We want not only to model the intensity, we want to model the polarization state as well. And there are quite a few effects that influence that. And actually, this line scattering, which we talked about today, leads to polarization in spectral lines. But we're not going to talk about it in the scope of this course. Okay, we maybe do something extracurricular, but not, there is simply no time, and it's very, very demanding. What we're going to talk about is Zeeman effect. And you know about Zeeman effect from your atomic physics and quantum physics classes, and you know that it's basically the interplay between the magnetic field and energy states of the atom. And we are used to the fact that Zeeman effect leads to the splitting of the line. But how many of you know, how many of you have heard for sure, but have you all heard that Zeeman effect also induces polarization? Do you know like if I was going to ask you in one sentence why, what would you tell me? Is it polarized emission or is it something else?
Trying to remember how that part.
Huh?
If you want to cover that piece.
No, I will cover that from there, but I just want to tackle your mind. Zeeman effect is very interesting, but it's very, we are used to polarization of the light through, for example, reflection on the lake, right? But that would be sort of polarized emission, because we know now that scattering and reflection is emission. But Zeeman effect actually is created through selective absorption in a way. That different states of polarization are absorbed in different amounts, so we end up with polarized radiation. And we're going to go through it not in too much detail, but I will provide you with a lot of additional reading because the details are a bit cumbersome. You can understand them through, for example, through classical methods, through quantum methods also, but there is a lot of analysis there. So basically, if I was going to go through all that in detail, I would be just copying the pages from books, and maybe we don't want that. So what I'm going to suggest probably is that you read just few things in advance, maybe, and then we can discuss. But I will cover phenomenologically what is happening. Like what is the splitting, how does the splitting work, how the individual components are polarized, and how they conspire together to give us the polarized radiation. And then what we're going to do is we're going to look at some restricted cases. And the most important for us, for understanding, is going to be the case where we have atmosphere which is permeated with a magnetic field which is aligned with the direction of propagation of radiation we are interested in. So, of course, radiation is always propagating everywhere, but we usually look along one direction, and we're going to be mostly interested in the magnetic field which is along that direction. And we're going to see that that magnetic field creates circular polarization, and we're going to see then how these things are related. And then we will also mention what's happening with the perpendicular cases, and we're going to do one full, very slow hands-on exercise where we will analyze circular polarization using some suitable approximations and really extract magnetic field from the observation. Okay? And then after that, I'm going to tell you what inversions are. And we're going to spend one whole class talking about inversions and how they allow us to simultaneously deduce magnetic field, velocities, temperatures, maybe even densities, and things like that in solar atmosphere. And I will also show you how visually you can detect these things, effects of some of these things in the spectra, and how inversions retrieve these. And yes, sir?
So that's going to be 2 weeks from now?
It's going to be next 4 lectures, yes. So we're going to have a lot of condensed things. But after that, then we are done. Yes?
So the Zeeman effect polarization is most of it comes from the quantum nature, right? Of how...
Yes. Vaguely speaking, yes, yes, but it's very hard to treat it in a course like this. So you could also, the easiest way to understand it is, so let's answer this and then we can say that we're done because it's almost 3:31. You could see if you do it classically speaking, spectral line comes. You can explain spectral line by looking at the electron as a linear oscillator. Okay, and you have interaction of that between that. You have like this restitution force. You have electromagnetic field, and then you can explain many things. You get how the electron oscillates from the classical oscillator equation. Then you do Fourier transform of the oscillation, and you get distribution in wavelength or the frequency. And that's actually how you get this Lorentz profile. That sort of analogous thing, like we obtained Lorentz profile sort of from the natural width of the line, from uncertainty principle. But if you do it this classically, you will really get it. And then you can actually write equations how that atom disperses and absorbs the light. And you will say that the absorption coefficient has the imaginary part and the real part. And the real part is true absorption, and the imaginary part is basically change of polarization state, right? Because it rotates the electromagnetic wave. And that can tell you a lot, actually, to that. So I think also one of the things that I should ask, I mean, we have that book, Introduction to Spectropolarimetry, where that is done in this classical way. But no, it's simpler, it's much simpler. Line the Genti is polarization in spectral lines, and that's full quantum, I think, throughout all the book. It's very hard because it also relies on this Raka algebra and things like the algebra, which is hard. But in Introduction to Spectropolarimetry, it's done in a classical way. It's a book by Jose Carlos del Toro Iniesta. It's a very nice book, very easy read, and a lot of practical and good information, and very super good for overall use. And we have a few of these, and I ordered a few of these extra, and I will also ask him if he has some of nodes of his own that he could share with us so that we can put on the webpage. But that was it. Yes, go.
Does the fact that the electrons are actually spiraling around the magnetic field, does that have an effect on?
Yes, but not here. It has an effect in the synchrotron radiation and cyclotron radiation, which means in radio, but also an X, right? Yeah. In these like super large or super low. Yeah. And
but not in like optical.
Yeah. No, in optical. No. These are like the large scale causes of polarization. This would be, and in that case, you get this huge amount of polarization. You can get like 70% polarized light. But that's really macroscopic effect. This is really microscopic effect here. You really look at individual electrons and what's happening to them. Very good. I'm happy that you remember that. Cool. Thank you for listening. Let's go to last.
You want a bike?
I don't have my bike. I left it.
You don't have your bike?
I left it at so.
Okay, do you want to take the bus?
I want to take the bus. Bye, people. See you Tuesday.
All right.